Then we did an example. We did projectile motion, kind of derived that, and then did a projectile motion problem. And then we laid this thing out and kind of basically laid out our strategy to begin with. Had an idea of what we were going to do, right? Came up with equations for of A in the X and Y direction, and then particle B in the X and Y direction. And in order for them to hit each other, you set the position of A equal to the position of B, so you end up with two equations and two unknowns. That's what we did right at the very end last time. These are our two equations and two unknowns, and we set this guy equal to this guy, and then this guy equal to this guy, and then we solve for the two unknowns, which is time and that initial velocity, which is the thing that we were after, we were asked to find, and then out popped a couple of answers in your calculator. I just put it in my calculator. There's a couple answers. Only one makes sense. One of them's negative time, and then there's the other one that's positive time. And then so I grabbed the one that made sense, and that's the answer. Okay, and that one is one where we started out with knowing the accelerations and the positions, right? And then we kind of worked our way to velocity and then to position. This next one, we'll do another example here. I said there's kind of two forms of these types of problems. There's one where you are given something about the accelerations, and in this case, we're given the positions as function of time, and then this way you go the other direction. Instead of integrating and going towards position, in this one, we're gonna start out with position and then take derivatives to go to acceleration and velocity. Okay, so in this case right here, this is another projectile motion. In this one though, again, they give us the position as a function of time. So the position of that thing is x of t, so 86 t meters is the position, and then y of t, the position of that, is given right there, right? And you should recognize some of the stuff in here. 4.91, that's g over 2, which is, we came up with that in our acceleration equations before, so in our position equations based on going the other direction. Okay, so it's right there, we were given that. It says, give us the acceleration vector. Okay, so the first thing we got to do is start taking derivatives of stuff, right? Because in this case, we're given the position and we're going to go the other direction towards acceleration. And acceleration is the second derivative of the position. All right, so we start out down here. I'm just going to write x of t is equal to 86t. That was given to us. I'm going to do x dot, right? That's going to be the velocity. That's just going to be 86. And then x double dot is going to be equal to 0, right? Taking the derivative of a constant gives us that. So that's ax, and this is bx. I don't know why it's flickering there, but it is. All right, so then that's the x direction. Now we look at the y direction. This way is a little bit easier, I think, a little more straightforward going this direction. Y of t, 96t minus 4.91 t squared. Do y dot, that'll give us a velocity. This is going to be 96 minus 9.82 t, right? Just taking the derivative of it. So 2 times 4.91 gives us 9.82. This is going to be what Vy is, and take the second derivative is equal to negative 9.82. And that's going to be AY. So not quite gravity, just some rounding error stuff going on in there. Right, that's one of the things we need right there. And one of the things we need over here. Right, so the first part said, what is the acceleration vector? Right, kind of solved both of these things separately, but really they're all the same thing. The acceleration vector is just equal to ax in the I direction plus ay in the j direction. So that just ends up being negative 9.82 in the j direction. That's the vector of it, meters per second squared. Right. We just kind of solve both of them and then kind of put them back into vector form. And again, you don't have to do the ijk. You can put it in like square brackets and you can define your vectors that way if you want. Okay, that's the first part. The second part of the problem said the velocity vector at t equals 0. So, second part was the velocity vector, v. That's driving me crazy. I'm gonna have to look at it. Right. Vx in the I plus Vy in the j. This is 86 in the I. So I just go up and I see what Vx is, right? That's 86. 86 in the I plus 96. Oh my God. 96 minus 9.82 t in the j. I'm going to try to redo this thing. Well, I'm not even plugged in and it's showing stuff. All right. All right, we'll try that now. 86 in the I, right? But the problem statement says, what is that at t equal to 0? Right? So then you substitute at t equal to 0. Everywhere there's a t, you put that in, so that's just going to be 86 in the I plus 96 in the j. Right? Ooh, I left my units off. I should put my units in the answer, though, meters per second. Third part of the problem. Right, those are pretty straightforward. What is the max height? How do you think I find the max height? Thoughts? Back to physics stuff. I wanted to figure out the maximum height this thing reaches. What would I do? What's going to be, yeah? Yeah. That's right. Yeah. Yeah, right. It's just it's going to do a little pause up at the top, right? So it's going to go up. So it's going to be at the time in which the velocity in the y direction is equal to 0, right? And then that's like right at the cusp, right? It's going up, its velocity's up, and it's right on the cusp, and its velocity's down. So it's right in between there, right? So that's not going to be the height, that's going to be the time. And then we take that time and we put it back into the y position, and then it'll tell us what that maximum height is, all right? Good. 3. Max height. So we go, we say, when Vy is equal to 0. So we write down that equation right there, which is going to be 96 minus 9.82t is equal to 0. Right? If you solve that, plug that sucker, I plug that right in my calculator just like that, and that would give us t is equal to 9.78 seconds. Right? Then I take that time and I put it back into the y position. Y of t equal to 9.78. And that gives me 469. Yeah, 469 meters. Right, that just gave me the position. That gives me the time. Once I get the time, I then have to go back and put it into the y equation, my position equation. That gives me that. Right. Then the last one is, what is the range L? All right. So thoughts on that one? How do I get how far it's traveled? Thoughts? Yeah? Yeah? One of you guys? Yeah?
When you figure out when y of t is
So then, you know, what we have this entire equation, right? That's what's given to us. That's what this is. And so if we want, right, how far it's traveled this way, I know that the y is going to be equal to negative 120, right? So I find where y is equal to negative 120. That'll give me the time that it takes to get to negative 120. And then I take that time and I put it back into this x position with that same time, and then it'll tell me how far it traveled. Okay, let's do that. You're good. Look at you guys. It's like little puzzles, right? Little puzzles. That's 4.91 t squared equal to negative 120. Right? This will actually give you two again, one negative time and one positive time. Right? And the only one that makes sense is the positive time. Right? The negative time would be this way, right? If this thing kept going this direction. And so you get 20.73 seconds. I just plug that sucker right into my calculator just like that. And then out pops 20.73 seconds. And then, so then I come back and I say x of t equal to 20.73. And what you get out of that is 1783. I always find these ones a little bit more straightforward, right? Maybe it's just because my puny brain can handle derivatives better than it can handle integrals, possibly. It's a little bit more straightforward going that direction. If you have a homework problem very similar to this, I think with the golf ball, it was golfing and they get the equations and you have to solve for some of those things. Any questions about that one? Okay. We're going to start moving into angular motion. And so that was just Cartesian coordinates. And this big picture stuff, we're still in kinematics, just geometry of motion. We haven't talked about forces at all yet. So this is all just geometry. We did 1D, right? And then now we're doing 2D, which is like in the X and Y direction, right? And then we just did Cartesian coordinates. Now we're going to do normal tangent coordinates. And then the last one, we're going to do polar coordinates, right? Okay. Part of this before we get to normal tangent, we have to talk about angular motion. Right? This is a huge theme in this class, the angular motion, right? Things that are rotating, right? And something that's rotating can have velocity acceleration too, right? If you have a wheel that's rotating slowly, it has velocity, right? But it's not like traveling someplace, it's just rotating around the center, right? That velocity. And then it can also have acceleration as well, right? That angular velocity and acceleration, what we're going to define right now, okay? So if something's rotating, that's all it is. I mean, it's drawn like this in the book. Or here. But really, it's just something that's rotating, right? What we're going to be building up to is rigid bodies are going to absolutely be rotating. There's pencil rotating through the air, sprockets, levers and things like that are rotating. They kind of draw it this way, though, to begin with, is to just say, all right, well, we've just got this vector E, and it's going to go from this position over to this position. Let's go ahead and draw that. All right, and it's going to rotate a certain amount. Right? And when it rotates, it has a speed when it rotates, right? And that right there, that speed, we're going to call omega. Right? And this should be reviewed. I think you did this in physics. You should have done something similar to physics. The angular velocity is what we call omega. And I guess I left out that that's theta. As the angle changes, the rate in which that angle changes is what omega is. Okay? So this angular velocity, let's define that. Like I said, we're going to call it omega. Omega is equal to the time rate of change of that angle that I just drew, which is d theta dt. That's the time rate of change of that. And then we'll call this theta dot. Okay? So that's how we're going to define angular velocity, right? The other thing that can happen too, right, is that omega can change, right? It can get faster, it can get slower, right? And so that is angular acceleration. How does that omega change? Right? That is called what we call alpha. Alpha is equal to the time rate of change of omega, d omega dt. Right? Or that could be thought of as d squared theta dt squared, the second derivative of theta. This could be theta double dot, or this could be omega dot. Right? Throughout the semester, those will get interchanged quite regularly. Right? Alpha is theta double dot, or alpha is omega dot. Either one of those things. Like I said, they get in all of our equations and everything. The book does it. We're going to do it. Homework does it. All that stuff. It just kind of interchanges those things. Right? It's the time rate of change of that omega. Right? So for example here, if that omega was slowing down, we'd have alpha kind of going there. It'd be decelerating. It could be acting that direction. And I kind of drew it opposite to show deceleration. And then we'll talk about signs in a second. We're going to introduce the right-hand rule. Any questions about that so far, right? This is you're going to get used to this. Right now, this might seem a little foreign to you, but we're going to use it a ton. Okay, so let's talk about vector notation, right? These things are actually, right? I mean, all like velocities, right? Velocities, accelerations are all vectors. They have directions associated with them, right? These two have directions associated with them, but kind of in a weird direction. They end up being in the k direction is what they do. Omega vector, right? 2D stuff. We're just dealing with 2D stuff right now. Later on, we get into 3D stuff. There's going to be x, y, and z direction. But in the 2D planar stuff, this is going to be omega in the k direction. The magnitude is omega, and the direction is in the k. Right? And so we're going to use the right-hand rule for this. What you do, right, just like this is going to come up a lot, but what you do is you put your hands in the direction of the vector that's moving, and then you rotate your fingers in the direction of omega, right, like that, and my thumb is pointed out, right? And so then my thumb is pointed out, and the way I have it drawn, x, y, k is coming out of the board, so it's going that direction, okay? How about for alpha, the way it's drawn right there? What does alpha end up being on that? Ends up being negative, the way I have it drawn right there, right? Because I take my fingers, point them in the direction of that, rotate it into the direction of alpha, like that. And now my finger is pointed in the negative k direction. So that alpha that I have right there is in the negative k, the omega is drawn in the positive k, right? Again, that's going to be right-hand rule we're going to use a lot in this class. It comes up a lot. Especially when we start taking cross products and stuff. Right-hand rule is big. I'll say as shown, it's negative. I used to make fun of left-handed people, right? Because if they have to use the right-hand rule, it's like really awkward because they're trying to do it with their opposite hand and they're trying to do it. And then one of them rebutted one time and was like, actually, we have an advantage because while we're doing the right-hand rule, we could be writing, right? So like if on an exam, they could be doing the right-hand rule and actually keep writing. So any lefties in here? There you go. See, look at that. You have an advantage over the rest of us. Disadvantage when it comes to using scissors. Advantage when it comes to using the right-hand rule, right? You ever been in one of those lefty stores?
Yeah.
Did you ever buy anything? Did you get something?
No, but DeWalt makes a left-handed circular saw now, so that.
Do you have one?
Yeah.
Is it nice?
It's so nice. Blinded by whatever I'm cutting is great.
Yeah, that's great. Good for you. Not very many lefties left. I mean, is the number of left-handed people increasing or decreasing?
It's stagnant.
Is it stagnant?
I know it's like 2,500 left-handed people die every year from using right-handed like tools and stuff.
Oh, interesting. Trying to wipe you guys out, right? The weak. Trying to wipe the weak out. Okay. All right. So then one more thing. One of your homework problems this week, 13,100. All right. I'm going to give you a little hint on that one. All right. In that case, it's an alpha is a function of theta. It's a circular motion one, right? Alpha is a function of theta. This is the same thing of acceleration being a function of position, right? So when we did our cookbook before, we said, we have 1D problems. There's one case where it's alpha is a function of position, velocity or acceleration a function of position. Here's a case. This is one of those ones. Acceleration is a function of position. It's not really in a form that we're used to because it's now angular motion, but it's angular acceleration a function of an angle basically, which is acceleration a function of position. And so to solve this one, you have to use this technique, right? This is the chain rule, which is equal to d omega d theta rather, times d theta dt, where this is omega. You got to do this. And just from years past when I've assigned this one before, people have missed that. Right? So you got to use the chain rule to solve that problem because it is acceleration a function of position. You may have gotten there if you would have noticed that, but I just wanted to point it out that this is indeed acceleration function of position. Okay. Any questions about that stuff? This is coming up right away, right? When we start talking about normal tangents, coordinates, this comes up. The other thing that we have to do that we're going to use in part of our derivation is what we do when we take the derivative of a base vector that is changing, right? So our next coordinate system, our coordinates are not fixed. Our Cartesian coordinates, our coordinates were fixed, so we took the derivative of it. It ended up being 0. That the derivative of something that's not moving ends up being 0, right? In this particular case, the next one, our coordinate system is moving with the particle, and so when we take the derivative of the base vector, it is something. So let's talk about what that's going to be, right? And so the textbook's got a big section on this, but we got this guy. Let's just draw it out here. We've got a vector, a base vector. We'll call it E hat t. A short time later, it rotates over to another position. Right, we'll call this E hat of t plus delta t. Just a short time later, it moves. All right, and so then it actually moves at a perpendicular to the original base vectors. That's just a 90 right in there. All right, this guy right here we're going to call delta E hat. Right, the change in the base vector. All right, and so some observations. The book goes through the full proof. I'm just gonna tell you, and you can trust me on this one. Delta E hat will be perpendicular. Right, so this little symbol means just perpendicular to E. All right. And so I left this part out. This is for an omega like this. So it's changing like that. It's perpendicular to the original, and that's not, that's not hard to observe, right? You can imagine, like the way I have it drawn here, it starts drifting away from that, but like immediate, like we're talking differential, like right here, that change is just going to be perpendicular, going to be straight perpendicular to that, right? And that's a key concept. We need that. So when we take the time derivative, that's going to come out of there. We're going to call that direction of E, we're going to call that normal, right? It's an N, it's normal to the position E, or that position vector. All right, so this is direction perpendicular. It's a vector that's doing it. Okay, so if we take the time derivative of that vector that's changing down here, it ends up being omega in the n direction. It's kind of a little bit of a leap there, but if there's omega, we'll get to this a little bit later. If you want the velocity of something, it ends up being omega times the moment arm that's going on. They'll tell the velocity at a certain point. Anyways, it's the change in that base vector with respect to time just ends up being d theta dt in the n direction. So we have a new direction, or in this case, it's going to be omega in the n direction. All right. So later on, and this is just kind of all the proof behind this is in the textbook if you want to dive in, but just trust me on this one, right? When you take the derivative of a base vector, it ends up being omega in a direction perpendicular to the original direction, right? That'll tell us what that derivative is. Right? Okay, so trust me with that. Let's talk vector notation down here. You could do the same thing. You could do this in vector notation. This is a cross product. So if I take the derivative of E, that base vector with respect to time, it ends up being equal to omega crossed with E. It's a cross product. We're going to use cross product a lot in this class. The way we do cross product, the way I like to do cross products, and we'll dive in later when we actually start doing calculations, but you take your hand and you put it in the direction of the first vector, okay? And then you curl your fingers into the direction of the other vector that you're taking the derivative of. And then the direction your thumb is pointing is the direction of that vector, okay? So in this case, omega crossed with E, so the way I have it drawn up here, omega's coming out of the board, right? Because we got this, omega's going like that, so omega's pointing out that direction. So I take my omega going out that direction, and I cross it with E, which is going that way, cross it with E, and then my thumb is pointing perpendicular. Everybody see that? Right. It's going to be a very recurring theme in this class. Right? I'll go over to you guys. Now. Right? So you go omega coming out like this, rotate in the direction of E, right? And then my thumb is pointed in the direction of N, what we call N, is perpendicular to it. Right? Again, we're going to get very used to using that throughout the semester. Questions? Okay. Let's get into what we're talking about. Normal tangent coordinate system. Sometimes you're going to want to use a different coordinate. A Cartesian, it's going to be your favorite. You're going to always want to use it, but there's certain types of problems that it would just be too hard to do in Cartesian coordinates, right? Especially like circular motion, something that's rotating around, cars driving around in a circle or something like that. Doing that in Cartesian coordinates would be a huge pain in the butt. Doing it in polar or normal tangent is helpful. I will say that there's a lot of, the normal tangent coordinate system we're going to cover is very similar to polar coordinates. In fact, I've often thought of just cutting normal tangent out because it is so similar, but they are slightly different, and the university wants me to cover both of them, so we're going to cover both of them. Okay. Normal tangent coordinate system or path coordinate system. Sometimes it's best to use when the path is clearly defined, right? So something that's traveling along a road, traveling in a circle, something like that. Coordinates are, as the name implies, the coordinates are normal and tangent to the path. And so let's kind of draw them on here. So if I've got a particle over here, right, and it's traveling along that path in that direction, let me write the coordinates. Again, the coordinates are attached to the particle and are moving. So in this, we got normal to the path and tangent to the path. So tangent to the path would be this, right? And normal to the path would be this. All right, so my coordinates in this case are right just like that. All right, we're going to call that ET hat. This is going to be EN hat. Okay, short time later, right? So it's traveling along that path. So right in that case right there, that's what my coordinate system is, right? A short time later, say here, right? My coordinates now are doing this, tangent to the path, right? And then normal to the path. And actually, in this case, the normal is going to go this way, and we'll define that in a second. ET hat and EN hat. This is what I was talking about. Your base vector is changing. So when we get to a point where we take the derivative of that base vector, it's not going to be 0, right? So this thing's going like this, right? It's going like that, and then someplace in the middle, it's going to be like this, right? And then it goes over, and then it flips over like that, and then it starts curving down like that. So that coordinate system, these guys are moving. En and Et are always changing. They're changing with respect to time, right? Which is, and you're like, why the hell are we doing that? We'll get to that. Okay, so let's define each of these terms. Et hat is a, trying to put a text in there. Oh. Unit vector tangent to the path. En hat and hat, that is unit vector normal to the path. Vector normal to path. This is where we got a little bit more to it. Pointed in direction of instantaneous. Oh man. A popsicle stick. Oh man, I don't know. Also, I don't know how to spell instantaneous. It's always embarrassing when you can't even have spell check help you because you've spelled it so wrong that it's like, oh my god, like what are you even trying to do? Like what are you trying to get me? I have to be full disclosure. I'm a terrible speller. I'm a doctor. Like if you're a terrible speller, look what you could be a doctor someday. But literally last year, I was trying to respond. A student of mine, Axel, who's your TA, he's also a bike mechanic, and he rebuilt my back shock of my bike. And then I was like, this thing is butter, right? That's what I was trying to tell him, this is butter. I tried to be cool. And for some reason, I did not know butter was spelled with T's. I thought it was spelled with D's. And so I was trying to spell, I'm on the mountain, trying to spell butter. And nothing, it's like, wouldn't it help me at all? I was like, what the fuck is going on? Like butter. And then I finally was like, did voice to text. That's what your solution, yeah. Voice to text, like butter. And it's like, oh, do T's. Oh, shit. This is a side note. So you have a terrible speller. It's okay. It's okay. Right? Use me as inspiration. Like, if this son of a bitch could do this stuff, I can do it. He doesn't even know how to spell butter. Who calls it butter? Right? It's butter. It's butter. Anyways, fair enough. Instantaneous. Center of curvature. No, there we go. Instantaneous center curvature. This is why that thing was pointed in the other direction, right? It points towards the center of curvature, right? So in this case, on the bottom left right here, the center of curvature is back this direction, right? When it comes this way, it's curving that direction, so it's pointed back towards the center of curvature. So that's why En is going back towards the middle, okay? Oops. All right, some more things. Let's define S. I don't think I drew S on here yet, but S is the distance along the path. Okay, that'll come in a little bit later. And then rho is the radius of curvature. What else is there? Oh, that's it. So S, we don't really need to draw anything, but it's just the distance along that path. If it goes from here to there, right, that position in between them is going to be S. And the radius of curvature is going to be this radius. Oh, what color is this? It's going to be this radius here, right? We call that rho. Right, that thing, at some point, it is kind of like circular motion. It is going around a center at one point. That center could be changing depending on what if it's a circle, it's going to be a fixed point. But if it's not, that curvature is going to be changing as we go along. But that instantaneous, that's why we say instantaneous in that direction, what is the curvature at that exact moment as it goes around that corner? And that's considered rho. That distance there is considered rho. S is the distance along the path, rho is that. Okay. So in this coordinate system, let's define velocity and acceleration. All right. So in this case, velocity is always tangent to path. So ET is, okay, so in the ET direction, always. So velocity, when we talk about velocity in this coordinate system, right, that coordinate system says that ET is tangent to the path, so all of our velocity is always in the ET direction, right? It has to be, right? There is no EN direction component of velocity. If there's EN direction, it means it's not on the path, right? And so when we define velocity, it's just going to be the time rate of change of the position along the path in the ET direction. When we do, you might be a little confused right now, but once we start doing some example problems, you'll see why we're doing it this way. We got to go through this first, though. Right? So the velocity vector is always there is no EN component. And so what I mean by these base vectors, right? Just like we wrote I, J, and K when we wrote down our velocities and accelerations, we do the same thing here. Instead of writing I, J, and K, we write ET and EN, right? Because those are base vectors. It tells us the direction that they're acting. In this case, the direction that it's acting, our velocity is always in the ET direction. Sure, ET is always changing, but we'll deal with that later, right? But specifically in this coordinate system, this is the answer. ds in the ET direction. ds dt in the ET direction. All right, acceleration now. So we take the derivative of the velocity. And I've been hinting about this all along. This gets a little more complicated. Acceleration is dv dt. The velocity, we have to put the whole thing in there. It's going to be dv in the ET direction. That is what velocity is. It's got both those things in there. Right? So it's v times ET. And so to take that derivative, we have to do the product rule. So we take the derivative of the first thing, leave the second thing alone, derivative of the second thing, leave the first thing alone. So that's what this does. So this becomes, take the derivative of the first thing, dv dt, dt, in the ET direction, plus leave the first thing alone, which is v, take the derivative of the second thing, which is ET hat dt. Okay? And this is where, right, so it kind of blew up a little bit. So it's got we've got two different components to this acceleration now. This is where, right here, we're taking the derivative of a base vector. On the right-hand side there, it's a derivative of the base vector. In this case, the base vector is ET, right? And we did something similar in Cartesian coordinates, but when we take the derivative of I with respect to t, that went to 0, and all these extra components went away. This time, this sucker doesn't go away. This is where that stuff we did before on the previous page comes into play. If we take the derivative of a base vector, right? This becomes this right here. And this becomes, so if we take d et hat dt, I'm zoomed in a little bit too much here. That's equal to d theta dt in the n direction, normal, which is going to be en hat. We'll say, see previous page. Right? Your previous page in the notes is where that came from. We said taking the derivative of a base vector. So that's what happens. Take the derivative of the base vector et, is just going to be omega, which is d theta dt, in the en direction, right? Because it says it's going to be the direction normal to et, right? And in this case, normal to et is the en direction, right? Just by definition of what en is, it ends up being that, right? Or we could write this as omega in the en direction. Right? So if you take that, this stuff, and substitute it in up above, you get this thing. I need to work on my spacing in my notes. Wasting a lot of paper. Right? I guess I should point that out up here. This is just a, that's v dot. Right, so if I substitute in that omega in the en direction, this is what we get. Right? So you get v dot in the et direction plus v times theta dot in the en direction. So you get two different components to your acceleration, right? And which should ring true a little bit, right, in what's happening. And so this should be somewhat familiar. Maybe not in this form, this isn't familiar to you, but this should be familiar that your acceleration has two components in it. Why would it have two components? Why does my acceleration end up with two components, two different directions? Yeah.
A central component and a tangential component?
Yeah, right. And so what is the central one? What's the name of that? Centripetal. Right? So there's a centripetal acceleration. It's not a form that you used to see in the centripetal acceleration, but that's what this is. That's what the en direction is, the centripetal acceleration. And the other one is the change in speed along the path. Right? And so there's those two different components. Or another way to look at it, or even simpler way to look at it, right, is if this thing is traveling along this path, right, it can have acceleration along the path, right? It could be, say you're in a car and you're stepping on the gas and you're accelerating along a path, like driving down a road. I would have stepping on the gas would be acceleration along the path, right? Because it's making my car go faster along the path. But then there also is an acceleration component associated with change of direction, right? If velocity is going in one direction and you change the direction of it, then there has to be acceleration, because velocity is a vector. If there's a change in the direction of a vector, that also is considered acceleration. And so that's why we get two components. One of them is the change in speed. The other one's the change of direction, right? And it makes sense that comes out of it. You've seen that before, just not in this form, right? So let's just make note of that. This is what we usually call change in speed. Right? And this is change in direction. And direction. Oh, well, I got some extra space this one. Oh, that's it. Okay. So what we'll do next time is kind of talk about some other form. Like I said, you haven't seen this form before, right? What you may have seen before is one of these other forms, right? One of these guys down here. V squared over rho, or rho omega squared. Like you may have seen those. V squared over rho, like that's your typical centripetal acceleration. Or you can write it in terms of rho omega squared. Either one of these ones are pretty commonplace, right? And so we'll talk about how we get to these. We'll talk about how we get to these next time, right? So you have enough to do your homework, which is due on Friday. We'll meet on Friday and just keep going with this stuff. Cool. Thanks.